final momentum is actually equal to the initial momentum. Once again, as long as the system is isolated. And we looked at a few different, and in what is called a collision, where do I define collision? I think it's on the previous slide. In a collision, which is just a short duration interaction, you can assume that the net force is going to be equal to zero. So, conservation of momentum is definitely applicable in a collision. And that's why we were able to do Bob running on the cart example. They interacted for a very short amount of time, at which point we can assert that the final momentum of the system is equal to the initial. And we also looked at a few different types of collisions. One is called the perfectly inelastic collision, where two objects come together, they stick together, and then move in unison. As long as you define your system as the collection of the two different samples, or two different particles, and the collective particle in the final state, you can say that your initial momentum is indeed equal to your final. The explosion was the second type of collision. It's essentially collision in reverse. So instead of particles sticking or colliding and sticking, a single particle essentially collides into many different particles, and that will be an explosion. And that will be another scenario in which momentum is conserved. We have to remember momentum is a vector quantity, so it needs to be conserved in both the x and the y components. And so the reason why, even though we went over momentum on Monday, the reason why it wasn't on the problem set and it won't be on the quiz tomorrow is because I did not go over a numerical example or an actual example using this two-dimensional idea. And so we're going to do that now. Where's my options? So we're going to do a conservation of example problem. So we're going to be looking at a three-piece explosion. Now, I know explosions go off into, a bajillion different pieces. Yes, you would be able to do this as long as you actually make note of all the bajillion pieces. Now, that's really hard, so let's just limit our analysis to 3. Let's say a 10-gram projectile is traveling east at 2.0 meters per second. And this projectile explodes into 3 pieces. One piece, let's say piece A, is 3 grams and it travels west at 10 meters per second. B is also 3 grams and travels 40 degrees north of east at 12 meters per second. Then the question becomes, we're given information about 2 pieces. I want you guys to tell me what is the speed and direction of the third piece. Okay, I actually didn't solve this numerically, so I don't know why I gave numbers. So I might have some of you guys, plug it in the calculator for me. All right, to begin, let's just make sure we're understanding the scenario properly. We have a single projectile that weighs 10 grams, and it's traveling east. 2 meters per second. Then this projectile explodes into 3 different pieces. Piece A is going straight west at 10 meters per second, and this is 3 grams. Another piece is going 40 degrees north of east, meaning this is east, and it's going north in this direction. We'll call this theta 2. This is also 3 grams. And the speed is 12 meters per second. The last piece, we're not given its mass, nor are we given the direction, so let's just call or give it a generic direction somewhere in the diagonal. Essentially, what we are asked for is the velocity of this third piece, we'll call it v3, is equal to what? Now, in this scenario, is momentum conserved? Yes, as long as your system is what? How do you define your system? Yes, if it's isolated, yes, but what is it?
Particles disperse.
Huh?
Particles disperse in many pieces.
Yeah, well, don't give me an action. I'm looking for a noun. What is your system? Which particle? Just this particle? This one? Or that one? Or this one?
Well,
All of them? So all of them right here? All of them here? These are 2 different time points. You're a time traveler? All right, it's this as well as this collectively. As long as this is your system that you have defined, yes, then the momentum is conserved. This would be your initial momentum. This collectively will be your final momentum. So some of the things that we know, we know the total mass. We also know the initial speed. This is, we'll call it the initial speed, v naught. Well, actually, it's the velocity. We know the velocity, we know the direction as well as the magnitude. We also know the velocity of the first particle. We know the velocity of the second particle. We're also given mass 1, when we're also given mass 2. And we're also given theta 2. I think that's everything. What we want is V3. This is equal to what? Well, to get V3, we can begin with conservation of momentum. Here we're given an initial state and we're asked about a final state. And from that, you really only have 2 options. It's either a kinematics problem or a conservation law problem. If you thought that it was kinematics, you can start it and you'll quickly find out that this was the wrong type. And so then conservation is where you want to go. So P naught is going to be P final. Or why do I, okay, well that's true, but okay, that's fine. Your final momentum, or your initial momentum here, you have a single particle with a mass of, let's say, m total. But momentum is mass times velocity, and it has a velocity v naught. And that is your the total momentum in your initial state. Then in your final state, you have contributions from 3 different pieces. Mass of 1 times velocity of 1, plus mass of 2 times velocity of 2, plus mass of 3 times velocity of 3. All right, I'm gonna move around some pictures to make myself more room. 1 second. There you go. Now we have to remind ourselves, momentum is a vector, meaning that we need to do it for each and every single direction that we have. We have the x component as well as the y component. So we must write an analogous conservation of momentum in the x direction. So we have in the x direction mass total times the velocity. Which direction, or this would be v naught in the x direction. One second. Which direction is it traveling? Positive x, so it is positive v naught x. Positive v naught x. And this is going to be equal to mass times velocity 1 in the x direction. Which direction is the first particle traveling? Right, negative x, so it'll be negative v1x. Plus mass 2 times the x component of particle 2. And notice we're going to have a velocity triangle, where this is v2, this right angle, this is theta 2, v2x then is v2 cosine of theta 2. But which direction is our x component? Right, it's positive direction, so it is plus v2x. Plus m3 times v3x. Now here we can make a few different simplifications. Your initial speed of this guy, you only have the x component. So v naught x is actually simply v naught, the initial speed. Likewise, your first particle, it's only moving in the negative x direction. There is no y component, so the x component is its entire, or the speed is its entire x component. So it's negative m1 v1, right? It's negative because it's traveling in the negative x direction. Plus m2 v2 cosine of theta 2 plus, this is simply m3 v3x. Now let's just assess, do we know each and every single parameter? Do we know mass total? Yes, it's 10 grams, we were given that. Do we know the initial velocity or initial speed? Yes, it was 2 meters per second. We know mass 1, we know mass 2, we know speed 1, we know speed 2. We also know theta 2. Do we know mass 3?
Yes.
Says yes, raise your hand. What is it? Okay, well, we're not directly given it, but we have what is called conservation of mass. And how did you guys get 4? The initial minus the 2 different pieces, right? The m total is equal to m1 plus m2 plus m3. Meaning, because we know originally it's 10 grams and 2 of those pieces constitute 6, 10 minus 6 is then 4, so mass of 3 is actually going to be 4 grams. So with this, we know what mass 3 is. Where mass 3, m3, is going to be mass m total minus m1 minus m2. The only thing we don't know is the x component. So, we know everything except v3x now we just have to do a little bit of algebra. V3x is going to be m total v naught plus m1 v1 minus m2 v2 cosine of theta 2 all over m3, which is going to be mass total minus m1 minus m2. So this is your x component. Yeah.
How did n1 go from being negative to positive in that final equation?
Because it's minus m1 v1 over here, so we need to add m1 v1 to both sides to cancel this. Then when we add it here. Yeah. So that's the x component. Now we have to do it for the y component. For the y component, it's pretty much the same thing. We begin by writing down the conservation of mass in the y component. So m total times v naught y, that's our initial. However, let's look at our schematic. Is there a y component speed in our original particle? The answer is no, so this entire term is simply 0. V naught y is 0. This is equal to m1 times v1y. Let's look at the first particle. Does that have a y component? And it does not, so that one is also 0. Plus m2 v2y. Now we need to look up here. Does this have a y component? And the answer is yes, it is v2y, which is v2 sine of theta 2. Right, from our velocity triangle. Plus m3 v3y. So we get 0 is equal to m2 v2 sine of theta 2 plus m3 v3y. Once again, we know m2, we know v2, we know theta 2, we also know m3. So now it's just a matter of a little bit of algebra. v3y is equal to negative m2 v2 sine of theta 2 all over m3, which is m total minus m1 minus m2. So that's a doozy to plug in the calculator. Yeah.
So we made it sine because we just assume that the angle is that direction, or how do we assume which direction the third angle is going?
The third angle? No. This sine comes from here.
Oh, okay.
Yeah. It is totally dependent on the second particle. Yeah, I actually didn't solve this or plug this into my calculator, but the velocity would then be v3xi plus v3yj, where the x component is all of that, and the y component is all of that. Now I asked you for the speed. Speed v3 is equal to v3x squared plus v3y squared, square rooted, right? That's the Pythagorean theorem. X component, y component, do the Pythagorean theorem on that. I also asked for the angle theta, which is the arctangent of opposite over adjacent, meaning the y component over the x component, v3y over v3x. Yeah. So if someone wants to give me the numbers, I would greatly appreciate it, but there's a lot here, so I might just move on. So conservation of momentum problems, really, you just set the initial equal to final, and then you just have to, make simplifications. Which information are you provided, which are not, and then you just have to do a little bit of algebra, and that's pretty much it. So it's pretty simple. There's not, I wouldn't say there's a lot of complexity involved, and it's, I would say, pretty straightforward. Most of the problems are going to seem identical as long as you guys give it enough practice. Now, where we're turning to now is another concept that is conserved. We just finished talking about conservation of momentum. Another topic that is conserved on top of mass is conservation, or is energy. So we're going to talk about what is called the conservation of energy. Well, let's first define energy. Let's see a show of hands. Who's ever been to the gym or play sports, and etc. Okay. You are always told to drink water, right? Does water have energy? Raise your hand. Who says yes? Who says no? Who's unsure? Okay, I still don't have everybody's hand, so I don't know what's going on. Does it have energy? Who knows?
It helps make energy.
Okay, yes, water actually does not have energy. But for your body to actually break down food to get meaningful energy requires water. Right? Water helps break it down. So, well then, what is energy? Energy, how we're defining it, is the ability to do work. Ability to do work. Okay, well then, what is work? What is work? You can't think about work in terms of how people are using it unscientifically. Now, it's still correct. I'm not saying that they're wrong or anything. However, when we're trying to define energy, we do have to be precise about what work actually is on the scientific level. Essentially, work, in terms of math, is force times distance. Force times distance. If something can apply a force and make it go some distance, that is considered work. You just did work onto something. If it makes anything move, then you are said to have done work. So energy is simply the ability to move anything. That's what it means. That's energy. Ability to make something move. Here, there are different types. Types of energy. The first one is energy stored in motion. The second one is energy stored in position. The third is energy stored in temperature. And the last is stored in, we'll just call it, the group is called chemistry. You can have energy stored in these various ways: motion, position, temperature, and the chemical nature. If it's stored in motion, it is called kinetic energy. It is called kinetic energy. And we call it K, or we'll call it KE, which is equal to 1/2 mv squared. If it's stored in position, it is called potential energy. Potential energy, we call it U. As long as it's from gravity, we use the notation G. So here, let me say this: potential energy, and we'll put in parentheses, in this one, it's gravity. There's a few different potential energies. The one that I'm gonna write here is just one coming from gravity, UG. And this has an expression of mgy minus some reference height. The one stored in temperature, we're not going to use. The one in chemistry, well, it is not a chemistry class. So we're going to neglect the consideration of these two other energy forms. But let's look at the kinetic energy. It is 1/2 mv squared. So the faster you go, the more energy you have, and your speed is actually squared. In terms of your potential energy, it is your mass times gravity times the height minus some reference height. Well, what is the reference height? Now, if I were to lift up my pen and I were to let it go, what would happen to the pen? All right, the pen's going to go down, right? The pen's going to go down. Because it's going down, and if I, let's say, some object was here, and the object, my pen hits it, the object can move, right? So there's work that can be done just from the fact that I place something high up. That's why when, let's say you're reaching for something, your jar, and then you actually knock it over, it's gonna go where? It's gonna crash, break, and go everywhere, right? Because there's energy stored in position. What this Y reference means is when I drop the pen from here, where is it going to stop? When it hits the table. The reference height would be the table. But whereas when I take a step back and then I let it go, where would the pen stop moving? When it hits the ground. So your reference height then would be the ground. This is simply just saying how high you are up from where it's going to actually hit whatever surface that's going to prevent it from moving. Okay, so you can think of the potential energy due to gravity, just how high something has been placed. Okay. Now we have what is called, or now we can talk about the conservation of it. Conservation of energy, or actually, I forgot to mention something. When we put both of these two contributions together, it is simply called mechanical energy. Mechanical energy. So we can come up with what is called conservation of mechanical energy, which states that E mech final is equal to E mech initial. Meaning 1/2 mvf squared plus mg y final minus y reference is equal to 1/2 mv naught squared plus mg y naught minus y reference. Now we're going to call this conservation event mechanical energy part 1 because there's going to be a part 2. Now let's do a simple example, a conceptual example with this in mind. So the total, essentially what this is saying is the total mechanical energy is conserved. The total mechanical energy does not change. Let's say you have 4 kids on 4 slides. Let's say slide A. Well, let's say all the different slides begin at the same height. Let's say slide A is very, very steep. Who wants to write this? All right, this looks fun. Slide B, let's say, is very, very shallow, but it's straight, and let's say it looks like this. In C, let's say it looks like that. In slide D, let's say it looks like this. 4 different slides. The question is, which kid will have highest exit speed? The kid from which slide will have the highest exit speed? Let's see a show of hands. Who says A will have the highest exit speed? Who says B will have the highest exit speed? Who says C will have the highest exit speed? What about D? All right, what about E?
Sure.
And the answer is E. They are all the same. But why is that? Well, as long as the slide begins at this height and ends at the same height, when the kid enters the slide, what kind of energy does each kid have? What is the energy? You only have at the very top. What kind of energy do you have? Yeah, do you have any kinetic? No, it's only, well, this would be your Y reference point. Each kid only has potential energy. Right? Does that make sense so far? But when the kid is down here, what energy does he have now? Does he have any potential energy? No, he's on the ground. Therefore, what is the potential energy all got converted to what form? The kinetic energy. They all exit with the same kinetic energy. So here, all began with only UG. All ends with only KE. Since UG is the same, KE final is the same. Now they're traveling at different angles, that is true. But they all have the same exit speed. It doesn't matter what shape it is. Okay, well, here, as long as we assume frictionless. As long as it's frictionless, they will all have the same exit speed because they began from the same height. All of that potential energy got converted to kinetic energy. Now, one thing to note is energy a scalar or a vector? It is a scalar. This v is not the velocity, it is the speed. Just the speed. So this is speed, not velocity. Speed, not velocity. Energy is a scalar quantity. Okay. So conservation of energy will tell us, yes, because everything began with the same potential energy, they will all end with the same kinetic energy. One thing to note is that K plus UG, or mechanical energy, oh yeah, question.
So in these equations for KE, is the V a lowercase, or how can we tell if it's next to velocity, or will it not be in the same equation?
No, velocity is this, speed is that.
Right. Thank you.
Well, so notes, let's just say mechanical energy. Mechanical energy is not always conserved. Mechanical energy is not always conserved. If friction exists, or if friction is present, then EMEC not conserved. Now, why might that be the case? Why, if there is friction, is mechanical energy not conserved? Yeah.
Maybe because you have more time with friction based on angle.
Well, energy, so there's no friction energy here. So just because there's some friction and you're spending a lot of, some time on there doesn't mean that energy's somehow going to go away. But, yeah.
Does it inhibit motion? And that changes.
Yeah, but how does it inhibit motion? That's the question.
It will like either slow it down or speed it up.
Yeah, but so there once again, there's no frictional energy. So where is the energy going? Energy has to go somewhere. Energy just doesn't magically disappear, or that will break the conservation of energy. Yeah.
Does it have to overcome the friction?
How does it overcome friction? Yeah.
Because friction opposes it.
Yeah, but you're still not telling me where the energy goes. Yes, friction leads to increase in temperature. What happens when you rub your hand really fast? It gets warm. Right, that's why you do this when it's like freezing outside, right? Friction leads to temperature. So mechanical energy is not conserved because some of that energy is going into thermal energy, which we do not consider mechanical energy. So if friction is present, then EMEC is not conserved because friction leads to thermal energy. So some of your mechanical energy, if friction is present, is going into heating up all the different molecules around. Now we're going to move on to mechanical energy part 2. And here we're dealing with springs and elasticity. I'm sure you guys have all played with rubber bands, and you guys should all know if you stretch it, then the rubber band is going to try to fight against you, right? It's going to pull back. So if stretched, the rubber band will pull back. This is the property of elasticity. So we say an object is elastic. If you stretch it, it will pull back. And the ideal or the most classical object that has elasticity is a spring. Springs are the prototypical elastic object. And we discussed that the force of the spring is equal to negative K times delta X, where K is the spring constant and delta X is deviation from equilibrium. Now let's think. You have your spring, and let's say you stretch it. When you let it go, what's going to happen? The spring is going to pull back. Guess what you just did, or what the spring did when it pulls back? It did some work. Right? It applied a force and actually made an object move. Therefore, there is energy associated with how compressed or how stretched a spring is. So there is energy associated with a spring, and that is a form of potential energy. So that we give the notation U. It is potential energy because it is associated with where, with respect to the equilibrium value, it is. Right? Potential energy is the energy associated with position. Energy associated with where that object is. And just based on the location of where it is on the spring, you have different amounts of energy that can be done. And this has a value of 1/2 K delta X squared. This is the potential energy stored in a spring. Thus, we get to conservation of mechanical energy number 2. E mechanical is the kinetic energy plus the sum of your potential energies. Meaning it is kinetic energy plus potential energy due to gravity plus potential energy of the spring. And this is the more general one, which encompasses the original. This would be conservation of mechanical energy, part 2. So the initials of these 3 is equal to the finals of these 3. So with energy being conserved, we can now look at some useful graphs that can convey to us quite a lot of information, and these are called energy diagrams. Energy diagrams. We can get a lot of information as long as you plot energy versus some useful parameter, such as, in this case, we're going to be looking at position. Position. You have energy versus Y. And we're only going to be considering gravity in this scenario. As soon as you drop, or let's say drop a ball, you immediately know what the total energy of the system is. Because when you drop something, you immediately know the kinetic energy. What is the kinetic energy? When you're just holding it? Right, 0. The speed is 0, therefore kinetic energy, remember, is 1/2 mv squared. If your speed is 0, you have 0 kinetic energy. But at the same time, you know the height. So you know immediately that this is going to be your potential energy, but also your total energy. This is also going to be your total energy, which we will call E total. Because at the original point, the entirety of your energy content is stored in potential energy. As soon as you let it go, you know that the height is going to go down, meaning you're going to be losing potential energy. So your potential energy is going to go down. This is UG. Well, then what's going to happen with kinetic energy? Well, we know kinetic energy plus potential energy has to be E total. So we know at this point it has to be down here. And when potential energy is 0, we know that it must be up here. And so it has to actually have this line. This is kinetic energy KE, which is the total energy minus the gravitational energy. Yeah.
So it's the sum of the line or the sum at the center of the two lines?
Any.
Okay.
As long as you add these two together, you're going to get this value. If you add these two, you're going to get this value. You add these two, you're going to get that value. At any point along the line, or at any y position, you can add up the kinetic energy and the potential energy contribution. You should end up with a total. Yeah.
The horizontal axis maybe a negative y-section.
Yes, that is correct. Or actually, yes. Well, yeah, that's true. We'll do. We'll do this. Y max minus y. There you go. So that's due to gravity. We can also draw something similar for springs. This time we're going to do it with respect to X. The system that we're looking at, let's say, is a spring attached horizontally. Therefore, it can go in either direction. If you look at the potential energy expression for a spring, notice it is dependent on the position squared. It is not linear position squared. Meaning, this is our equilibrium value, it's going to be parabolic in nature. So this is parabola. And if this was our total energy, E total, this is U spring, what would our kinetic energy look like? What would our kinetic energy look like? Well, when our potential energy is up here, the kinetic energy must be at 0. Likewise, when this is up here, our kinetic energy must be down here. But when our potential energy is down here, the kinetic energy must be up here. And potential energy plus the kinetic energy must always add up to the total. And that occurs if you get an upside down parabola. Yeah, question.
Is the top of the parabola for KE, is that also equilibrium? Or no? 'cause it's not
Equilibrium
measuring
occurs at this x value.
Okay.
Equilibrium happens at that x value. But I'm glad Sam asked the question, because this allows us to talk about a very important phenomenon called equilibrium. Who's heard of this term before? Okay, right. Pretty much everybody has. Well, what is it? What is equilibrium?
All forces and all energy cancel each other out.
All forces and all energy cancel each other out. Incorrect. Yeah,
Is
Matt.
it when F net equals 0?
Not when F net equals 0. Wow, so you guys have been using it without knowing what it is for all this time?
When an object is at rest. Or
Okay, when an object is at rest would be at equilibrium, but how can you predict when that will be? When will an object be at rest? Yeah.
when, I was thinking of the pulley system that we did in lab, when the force of one object equals the force of another object.
At that point, if F net is equal to 0, an object in motion will stay in motion. So you can still get a condition when that moves, so the net force being equal to 0 is actually not equilibrium.
Is that different than what was going on?
That is considered mechanical equilibrium, but that is not equilibrium in general. Right now, we're not talking about just mechanical equilibrium, just the idea of equilibrium. What is it? Yeah.
So it can be like when the energy, like there's no potential or kinetic energy.
Okay, now we're getting close. Equilibrium is associated with potential energy. It is when the potential energy is what?
Minus.
Okay, who says 0? Raise your hand. Fortunately, that's not the case. Equilibrium is where potential energy is minimized or minimal. That's why at this point we have we have what is called an equilibrium position. We have what is called an equilibrium position. Because you can see here that the potential energy is indeed at a minimum value. Okay. So let's talk about going down this rabbit hole. Except it was an intended rabbit hole. So equilibrium position. Equilibrium is defined as a state in which system is considered stable. But once again, what does stable mean? This is when U is okay, well, we're going to put where U is minimum, except when the slope of U is 0. That's actually the more technical definition. So it is stable when the slope of U is 0. Slope of the potential energy. Now, how is this? Well, actually, let me draw the graph first. And we can identify the equilibrium states in an energy diagram. So let's say we had an energy diagram that looked like this. How many equilibrium positions do we have in a system that has this energy diagram? Who says 1? Raise your hand. Who says 2? Raise your hand. Who says 3? Raise your hand. Who says 4? Raise your hand. All right, now it is 3. There's one right here at, let's say, x1. There's one here at x2. There's one here at x3. At all 3 of these points, the slope is 0. Okay. However, not all of these are what is called stable. Are these equilibrium points? Yes, but they do not have equal stability. Now let me put it this way. You can think of this as like the contour of a mountain. Okay, it's like the height of the mountain. If I were to place a ball, let's say right above x1, so right here, what's going to happen to the ball? It will stay, right? It is considered stable. What about if I put a ball right here? Where's it going to go? Or which direction is it going to go? It's going to go. Where's the final location going to be?
East.
Huh? East?
The right is
Well, okay, which x position is it going to end? Who says x1? Raise your hand. Who says x2? Raise your hand. Who says x3? Raise your hand. Who says something other than those 3? Raise your hand. It will end always in x1. Why will it not go to x3? This is where understanding energy helps us. The potential energy is right here, meaning that is the total energy. This ball will never ever make it above unless somebody kicks the ball higher. If you just let it go, it's going to go up and then stop at this point and then change direction, and essentially it's going to oscillate back and forth right here until, of course, friction is going to take it down, and the final location will be at x1. Yeah.
Does it only require, or is the only way to make it more fixed to kicking it from that spot, or can you move it higher up?
Yeah, you can move it higher up, but I asked specifically about me dropping it from here. And this is how equilibrium is different than F net being 0. If you put a ball right here, yes, F net's going to be 0, that is true. But the net force being equal to 0 will not make it so that you're going to be oscillating back and forth around this point. But in equilibrium, it does. Except, what happens at x2? Let's say I put the ball right here. What's going to happen to it? The options are it goes left, stays in place, and goes right. Who says goes left? Raise your hand. Who says goes right? Raise your hand. Who says stays in place? Raise your hand.
If you place it perfectly in the middle.
Yeah, I place it at x2. It will stay in place. That is why it is considered stable. But let's say instead of right at x1, you put it slightly to the left, what's going to happen? It's going to go, where would the final position be? It's going to be at x1. What about if I place it slightly to the right? Where is it going to be? X3. Clearly, there's a difference between x1 versus x2. In x1, if you put it slightly, deviated from x1, it's going to land back at x1, right? But at x2, as soon as you deviate slightly, the deviations are going to go further. So x1 and x3, these are called stable equilibrium. Whereas x2 is defined as what is called metastable. It is metastable because technically it is. If you put it at exactly x2, it will stay there. However, because of how it deviates, or because of the behavior around it, we do put it in a different category. So stable equilibrium is deviation from equilibrium will return to state. So essentially, any deviations will get it to return back to its original state. A metastable occurs when any deviation from equilibrium leads to further deviation. Deviation from equilibrium will lead to further deviation. Now let me ask you guys a question. If I place the ball here, where would it go? Where would the final location be?
X3.
Yeah, at this point it would be x3 because it could go down and it has enough energy to overcome this hump. So we'll do this, go down, and then it will go all the way up here, and then it will kind of oscillate here, so on and so forth, until it finally reaches right here. And so equilibrium happens whenever there are competing forces where one's going to win or one is going to lose. And ultimately, this is what many people say governs the world. Well, as believers, we understand that to mean how God actually created the universe, how God is keeping things in order. One group says it's force, right? Newton's law of forces. Why do objects do what it does? Well, it's because forces are being applied. A different group says, no, it's actually energy. Things, like nature, is going to do whatever it does to get to equilibrium, meaning it's going to do whatever to get to minimum energy. Now, which one is right? For me, they're just two ways of saying the same thing, because conservation of energy actually comes from force, comes from Newton's second law. But for the derivation, we need calculus, so that's why I skipped it for you guys. So they're kind of one and the same. However, nature does tend to go toward minimizing potential energy. Why does, when I drop the pen, where's it going to go? Down, because down is where you minimize potential energy, right? Yes?
I'm a little confused by that logic though, because if the universe is designed to make it so there's no energy,
No. The universe was not designed so that there's no energy. The universe was designed to bring glory to God.
Okay, but
Right.
if everything, why would anything exist if everything creates energy? Like.
No. Energy is conserved. Nothing creates energy.
Okay, but.
Energy is only converted from one form to another. What's trying to be minimized is potential energy. essentially, I know as humans, we want more energy to do stuff, right?
Right.
But as non-sentient things, as soon as it has potential energy, guess what it's going to do? Immediately spend it.
Right.
So if it has potential energy, it will use it, so it's going to go towards minimizing that potential energy.
So
That's why as soon as I let it go, pen's gonna go down because it's going to expend whatever potential energy it has.
So is it the ideal system to just not have anything exist at all, because then it's in equilibrium forever?
I don't follow the argumentation.
I was confused as to how they think that.
I'm not trying to use this as a proof of God's existence,
I'm
because
just-
that's not where I'm trying to go with this, but yes, this, as all the science is revealing, this does seem to be one of the principles that have yet to be refuted. So as believers, right, this is just understanding how God actually created the world. This is how he is keeping it in operation. Right. Yeah.
Can you give like a specific definition for potential energy?
Stored in position.
Stored in position.
Energy stored in position. Right, I gave that definition. If it's gravity, you're positioned with respect to gravity. If it's with respect to a spring, it's with respect to how far it is deviated from equilibrium. So potential energy is just where is it, and is there energy associated with it?
Okay.
So that's why it's going to go towards wherever the potential energy is minimized. The location where it's minimized, that's where it will go. That's why chemical bonds form, things like this. Alright, well this is all I got to in calculus-based class, so we will end it here.